Good morning, all. Today we're going to talk about voltage and how that works depending on whether you put your batteries in series or whether you put them in parallel. We've got a lot to do today, so let's jump right on it. Before we start the discussion, you are going to hear the word potential energy a lot. And potential just means the ability to do something. And so we like to think of potential, or we like to define potential energy as stored energy. Stored energy. And this can be stored in a number of different ways. Here are there's two skiers. You'll notice that the slope of both of the hills that they're on are the same, but this is a higher slope than this one is. So this skier number one has, if you just imagine, I think most of you are skiers and snowboarders. If you have a long steep hill as opposed to a short steep hill, by the time you reach the bottom, you're going to be going faster in the long steep hill than the short one. I think you can identify with that. So stored energy can be stored energy due to position, or for example with springs, compression, or chemical. And chemical includes what we're talking about today. Okay, so who do you think has the greater potential energy? This guy here, skier one, because he has a greater height. Okay, so it turns out, we all know, let's highlight colors, so I'm going to break this out, talk about potential energy, and now we want to talk about electric potential energy. Okay, so we already know that electrons have a charge, but they also have a certain amount of potential energy. Okay, the only way you can measure, though, is to measure the change in energy. You can't measure the energy directly. You can only see how much they give off when they do something. So change in energy. Okay, and the change in electric potential, energy, should have three lines there really, is called voltage. And you've probably heard that term before. And we measure it in, we use the symbol capital V, and that stands for volts. Okay? And it helps to think of voltage as a person who is high diving. Okay? So we think of a person who is high diving. Not that I'd ever high dive. I can barely swim, let alone high dive. I know. I'm 66 years old and I can't swim well. Give me a break. Can you measure? The question would be, can you measure their potential energy before they jump? Oh, jeez, what am I doing? I just got a ding on my laptop and it's distracting me. So I apologize for that. Can you measure their potential energy? Before they go. Now the keyword, oops, I'm sorry. I have to pay attention. If you need to pause, pause, and then fill in. The key word here is measure. The answer is no. You can't measure anything here still. You'll find out in later courses that you can calculate it, but you can't measure it. Okay? So, in the voltage high dive analogy, this same thing is true in an electric circuit. Same is true in an electric circuit. We can only measure the difference in the charge as it starts flowing. We can only measure the difference in the charge as it starts moving. And basically, the higher the dive, the more energy is produced. The higher the dive, and I know you get that. If you guys, any of you guys have done the cannonball, you try to get as high off the board as you can, so you can make a bigger splash. And the bigger splash is related to how much energy you hit the water with, right? I know you know this. So a battery raises the voltage, a load reduces the voltage. So a battery's job is to raise the voltage. And a load, like say a light bulb, reduces the voltage. Okay? Now we'll diagram this out. We'll make more sense and present it in a slightly different, more diagrammatic way. But the idea is that the energy or the voltage comes from the battery, and it's used by things like lamps and motors and things like that. So that's all we're saying right now. So just to give you a sense of when we're talking about volts, if you have two cells, this is actually not a good word. Two cells, and the two cells, when you put together, makes a technically makes the batteries, but we'll call things that you put in your, I was going to put in your Walkman. Now, things you put in your flashlight, we'll call those batteries too. So two batteries, generally they're about 1.5 volts each. Okay, and so if you put them in series, if you put them one after the other, it produces around 3 volts of electricity. Not quite, but let's say it does. And this is common in things like we already said in flashlights. If you the voltage in your plugins in your walls in the wall in a Canadian home is 120 volt. Not enough. Well, in certain circumstances it could kill you, but it's not common. In England and other countries, the voltage is 220, and that will kill you. Okay. The big transmission lines that you see going up the side of mountains and supported by huge steel girdered poles or not antennae, but structures. These are called, first of all, transmission lines, because they're transmitting them or carrying them from a source to the end users. Okay, so that's what we mean by transmissions. They're about 250 kilovolts. 250 kilovolts. Okay, small k, big V. And that, if you translate it out, every a kilo means 1,000. So this is basically 250,000 volts. Okay. The Van de Graaff capacitor, or it's a capacitor because it builds up charge on a dome, but it also generates at the same time. So you'll see the word generator and capacitor used interchangeably. They can produce, believe it or not, about 2 megavolts. Now, 2 megavolts is actually 2 million volts. And that's a lot of kick. Okay. The reason why you can put your hand on it and receive the built-in charge and it does not kill you is because it is building up on you. It's not flowing through you. If you were to put one hand on a Van de Graaff capacitor and one hand on, say, the pipe, or like a water pipe, it would kill you. It would outright kill you, because the voltage is now going straight through you. Okay, let me see now. Voltmeters. Voltmeters. I've got a picture here. Voltmeters. We looked at multimeters the other day, and so a voltmeter doesn't look much different than we looked at ammeters the other day, and a voltmeter doesn't really look much different. In fact, most meters today are like this guy in the middle, the yellow guy, who is a multimeter, and he can measure both voltage and he can actually measure voltage. He can measure current in amps. He can also measure resistance in ohms, which is something we'll talk about later. These other guys do basically the same thing. Depending on what you put your setting at, you can measure different things. So this one here is just a digital version of this guy here. You get a reading as an analog. This guy you get a digital, depending on where you want to set these dials. This guy here is a flat-on voltmeter. The only thing he measures is volts. And you can just barely see because of the shine. But you can also see that it has multiple tie-down points, and so depending on which ones you hook up, it will give you different ranges that it can measure it over. Okay, so one may only be able to measure up to, what's that? I can't even read that. It's so small. Say point. So this one's between 10 and 30 volts. Like if you have it, say on this one here, and a wire attached to here and a wire attached to here, you can measure 30 volts. If you have a wire attached to here and a wire attached to here, it looks like it measures to 3 volts. And if you have one attached to here, it only measures to 1 volt. And what does that mean? Well, that means that if you have these two, this will detect a very small change in voltage. So very small. This one will detect medium changes in voltage, and these two will detect large changes in voltage. Okay, so that's really what it means. Really, it would be ideal if we could be in the lab. I could actually, because I've got some of these guys, and we can actually play with them. So if I had a 1.5 volt cell, and I hooked it up to these two things, you might see the needle just budge a bit. Might just go, and that's it. If I had it, on the other hand, if I hooked it up to these two, because these two only measure up to 1 volt, this needle would go right over and be sitting trying to go further, and it wouldn't be able to go further. Okay, so these two measure small voltage differences up to 1 volt, these up to 30 volts. Okay, so not that you'd ever use these things. These things are no longer really in use, other than in laboratories or at all. Multimeters is what is used nowadays. Okay. Anyway, to measure voltage, you need a voltmeter. Oops, I'm too close. Oh, that's too far away. Try it again. Ah, I'll get it right. Okay, so to measure voltage, you need a voltmeter. To measure voltage, you need a voltmeter. Okay? Because voltage is the measure of the change in energy, you need to connect the voltmeter in parallel. And I'll show you what we mean on the diagram, but let's get the notes down first. Because voltage is a measure of the change in energy, you need to connect a voltmeter in parallel. Connect the voltmeter in parallel. Across a battery or a load to measure the difference. Okay, so this is these are two cells, each one is 1.5 volts. So what that means, if I was to take a voltmeter and I was to put it here, put one wire here, this is going out to the voltmeter, because this is 1.5 volts, and this is what this would say, this would say 3 volts. That's what it's going to say. Okay, because I got 1.5 from here, 1.5 from here. This is in parallel because you have two wires that are going side by side. The ammeter, which measures the current, it's like a counter of how many electrons go by. So the electrons come out this side, and they're going to go through this circuit like this, and most of them are going to go through this lamp and come back. Okay? What's going to happen here is that the energy that those electrons have are going to cause this lamp to glow. And if I was to measure in the voltmeter how much the voltage difference is, this would also say 3 volts. Okay? Now notice this is it's about 3 volts. There's a little bit of an issue here. And the reason why this is that right here at this wire, some of the electrons go this way, but most of them go that way. The little bit here says this is, say, this is measures how many volts are here, and it measures this measures how many volts are at this junction, and it measures how many volts are at this junction, and basically it subtracts and says, oh, 3 volts. That's because only a little teeny tiny bit goes here, and most goes through there. Okay? So ammeters are in series because they have to count the electrons as they go by. Voltmeters are outside. They're parallel because they have to measure the difference between the two sides and record that. Okay? Okay. This says draw a quick sketch of 7 and 8 from your notebook, and so that's all it's asking for you. So you can find that these two are what they're referring to, and yeah, I'll let you do that later on, or if you wanted to pause and do it now, you could. Okay, so what have we talked about so far on this page? We've talked about the voltmeter, and we have looked at series and parallel combinations of cells, and now we're going to talk about the difference between series and parallel combinations. Okay, so series actually, I'm going to get you to pause right now. I will get you to pause. I'm going to get you to draw these and then restart this. Okay? So I think this is all that's really necessary. My art is not great anyway, so I'd rather just put the words. The pumps, of course, are the batteries that are increasing the energy. The pumps, the waterfalls coming down, that is the load, like for example a lamp or stuff like that. Okay, so notice that the water pumps connected in series allow the water to go twice as high. Okay, so connected in series. Oh, I didn't write here, this is parallel. Sorry. Okay, so notice that the water pumps connected in series allow the water to go twice as high. So electrical or electric cells, batteries that are connected in series allow us to multiply the voltage. For example, if I attach, let's say, 4 1.5 volts, so 4 flashlight batteries in a row, and if I attach those in series, your new voltage is going to be 4 times 1.5 volts. It's going to equal 6 volts. Okay? Okay, so the parallel is different. So I know where you need to write the top here because somehow it got lost. So up here in parallel, okay, they have twice the amount of water because each pump carries the same amount of water. So they have twice the amount of water but it is only 1 pump high. So with electric cells in parallel, the voltage is not increased, but the cells can either have A, more current, or the batteries would last longer. So there's a trade-off. I'm going to pull up the other. I'm going to pull up that picture again, and let's look at this together. Okay, I know this is diagrammatic and it's looking at water instead of other things, but it does help a bit, at least in my mind. So if you cut, no, that's not going to work either. You need to look at the first one. Okay, so dumb light. So the water that is being pumped from the bottom here, the water that's being pumped up here is then being pumped up to this height. So there's not a doubling of water, it's just the same water that's just going up. But because you have these in series, it gets twice as high, so this thing can fall farther, as it were. So there's more voltage, or there's more energy of the falling water. If you look at this one now, you can see that you've got 2 pumps. They're only 1 pump high, so there's not as much energy to be used. But notice the difference. You can just look up here in this corner here. You see how much water is in these containers as opposed to here? Well, that's trying to get you to understand that because you've got 2 pumps running out of the same source, you're getting twice the amount of water here. So your current, in other words, your current goes up, but the energy, the voltage does not. Okay, now this may be a bit of a challenge for you to translate it across from electrical to electrical, but at least it's a help, I think, anyway. So what is on deck now is you need to look at your, if you don't have an actual textbook, there's the text material below, and check that out. And for homework, I want you to complete. You got a lot of work to do, so you've got about 30 minutes. Okay. I want you to do up to here, and then when we come back, when we come back on next day, you know what, these are, no, when we come back next day, together we will work through the CYU questions, the CYU questions. So I only want you to do up to this line. This is on page 15. And then next day we'll come together and we will work through this together. I'll do one. I'll get you to stop, do it, and then I'll do it. And then so we'll correct these together. We'll do these together. And then we'll go on and we will look at resistance. Resistance is futile, okay? And yeah, so I'm sorry I was so close there. So this is page, again, this is page 15. Only do up to where it says CYU questions. All of these questions are from your textbook. You can all copy them right out of your textbook. Up to here. Next day, you and I together will work through these things, and then we'll introduce the idea of resistance. Okay? Okay. Well done. Talk to you later. Bye now.